OK, so now let's start talking about how to leverage different more techniques to get a lot of the performance that we received in an out-of-order superscalar, but in a VLIW processor setting. And we're going to break this sort of into two different things. Dynamic events, so things that happen in the processor that you can't necessarily, or you can't really do anything about statically. It's really hard to do anything statically about it. You just don't know what's going to happen. Something like a interrupt or an exception happening. How can a compiler know where the exceptions are going to happen? It's just not really possible. And then we'll talk about speculation, which an out-of-order superscalar does. And a lot of the things that fall into this case, actually we can add things to classical VLIWs to get us closer to getting those performance improvements or the instruction level parallelism improvements that you can get from speculation. And we're going to talk about sort of two different types of speculation today. We're going to talk about how to move or speculatively move instructions over branches. So in particular, this actually gets really interesting with loads moving across branches, because you have a load, and you want to move the load as early as possible. You want to pull the load up early into your program so that if it misses in the cache or it has to go out to main memory, you can hide the latency while you're doing other things. We're also going to talk about speculation of speculating that two memory addresses, one of a load, let's say one of a store, or you could also think about this as loads with loads and stores with stores, but we want to reorder those. Similarly, because we want to get sort of loads started early and stores started as late as possible, so we have enough time to do the computation we have when we do the scheduling. And remember, in VLIWs, we're doing all this scheduling statically in the compiler. And as you may recall, from an out-of-order superscalar perspective, when you try to do load-store speculation and try to reorder loads and stores dynamically in an out-of-order superscalar or some sort of superscalar processor, you need an extra structure to figure out when you made a mistake, when you reordered something that was not a valid reordering. And we're going to have to add that same structure into our VLIW processor, or a very similar structure. So let's start off by talking about what the compiler has to do, or how the compiler even starts to think about this speculation. So I wanted to introduce a topic here from compilers. And this is sort of an introduction to how we schedule for VLIW, the nitty-gritty of what the instruction scheduler or the back end of the compiler is going to be doing. So here we have two pieces of code. We have before code motion and after code motion. So what is code motion? Well, code motion is reordering of instructions in order to tolerate the latencies of the instructions, or to do something good. So it might not just be tolerating latencies of instructions. It might also be reordering for alignment issues sometimes. Sometimes branches can only happen on certain alignments, or the performance is better. So, but roughly, we're trying to reorder the code or do valid reorderings of the code. We can't just move a read after write dependence and move it someplace else. We can't say, instruction A reads the result of instruction B. We can't move A before B, because it just wouldn't make any sense. But a lot of times, the compiler has some flexibility in what it can move around. OK, so let's look at this example case here. We have a gobbledygook of code. And what we're going to try to do here, well, two things to note. One, this branch at the end is dependent on register 16. Register 16, where does it get computed? Does it actually get computed anywhere in here? No. We're also saving away register 16. OK, so does register 16 get computed? Maybe not, but we probably want to give it as much time to be computed as possible. Some other things going on here. We have a load. OK, well, the load What if the load cache misses? Well, this next instruction here is directly dependent on that load. So we probably want to give it as much time as possible to execute. So traditionally in code motion, you want to sort of push the loads up and push the stores down. Well, we're going to do this, if we were to push the loads as high up as possible and the stores down as possible, we're going to move a load and a store past each other. And the question comes up, what if this value and this value, these two addresses, are the same? Well, so let's assume that they're not, and let's assume the compiler can somehow prove they're not. So you should be able to do code motion here where we're going to rejumble all the instructions, and we're going to push the load up and push the store down, leave the branch at the end. So we've done some code motion. The next thing we're going to want to do is we're going to want to bundle or schedule the instructions. So when I say bundle, we're going to take several operations and pack them together into one VLIW instruction or one VLIW bundle. And we denote that here with these braces to say these execute parallel or at the same time. So first, you're going to sort of want to do scheduling, and then you're going to want to somehow bundle non-dependent instructions together. There's been a couple algorithms that have tried to do sort of scheduling, code motion scheduling and everything, and bundling together. Those don't always work out as well. So most of the VLIW compilers now will actually do the code motion and the scheduling first, and then they'll do the bundling at the end. OK, so let's look at our first technique here to get at instruction level parallelism, and our first type of speculation in a VLIW processors. So what's our challenge here? What's our problem? Well, our problem is the branches, or the presence of a branch, rather, is going to restrict the forms of code motion the compiler can do. So we have a branch. We have some code after the branch. If you have, let's say, an add instruction, that's pretty easy to move it before the branch. OK. How about an instruction which can take a fault or take an interrupt? Loads are a good example of one of those sorts of instructions. How is that possible? Well, a load can take a page miss or a page fault. It can try to access some value which is not mapped in by the operating system. So let's say we take this load and we move it above the branch. OK, that's not too bad. Now what happens if that load takes a trap or takes an interrupt that was never supposed to happen? In correct program sequence order, the branch was going to branch around the load. So the load was never going to execute. But all of a sudden, the load got moved up, and the load executes. And it takes an interrupt. Well, your program crashes. It takes either a segenv or a bus error if you're on something like a Spark system, or you're basically taking a segmentation fault. Even though nothing went wrong, this branch was supposed to protect this load from never executing. So R1 here, let's say, just gets loaded with some bogus value if the branch is taken. And the compiler knew that, and the programmer knew that. But all of a sudden, the compiler decides to reorder things and has moved the load up. Now that, because it wanted to try to get more performance, this is something that you can do in your out-of-order superscalars also. The out-of-order superscalars are going to pull non-dependent loads up in the program and try to move them across branches. But in out-of-order superscalar, if you pull a load up and it does something wrong, it was speculative state. You just don't care about it. So we need some way to have loads that don't hurt the system. So it's a similar sort of idea, but we can't move this load above the branch because it might cause some sort of exception. So our solution to this is we're going to add special instructions, special versions of the instructions which don't take faults. So if the fault were to happen, it sort of remembers that the fault happened, but it doesn't actually interrupt the process. And this allows us to pull some of these instructions before branches, or reorder, perform code motion statically at compile time. OK, so let's take a look at this example here. How would we go about doing this? OK, so we're going to move the load up. So let's say we move the load as high as possible. We move it above these two instructions, instruction 1, instruction 2 here. And what do we need to do? Well, if you note, we don't have the word load here anymore. We have load.s. So this is a speculative load, which has different semantics. This load.s never causes an exception, even if it has like a page fault or a null pointer exception or unaligned memory reference or anything like that. It's not going to actually take that fault. Instead, it's just going to sort of remember that. And this is typically done if you look at something like Itanium, which is this is a sort of code sequence out of Itanium processors. In Itanium, what they're going to do is they're going to the destination of the load, in this case R1, is going to be set with a poison bit. Itanium, this is actually called not a number. And what that means is the destination register of the load is marked as not there, or that it's not a thing or not a number. And what's important about this is when you go to use that value, that's when you take the exception. So let's take a look at an example of this. What we do is down here, where the load originally was, we put in a check speculative instruction. And it uses R1 here. So what this is going to do is it's going to check the value of R1. And if R1 took a trap or exception and there was some problem with it, we can jump to fix-up code. So there'll be some other piece of code somewhere else we can branch to. And that fix-up code is going to re-execute the load and make sure everything is OK. And then jump back to the use. So it's speculation. We try to prove and we try to make sure that the common case, when we pull this load up, nothing bad is going to happen. But we put a check in just to make sure that this is the case. One other thing I wanted to point out here is these poison bits, or these not a numbers, they propagate. So why is this important? Well, what that means is, actually, I want to correct something you said a little bit here. If you try to use R1 somewhere else before you do a check, the not a number propagates. It doesn't take a trap. It only takes a trap, or only jumps to fix-up code when you go to actually do the use, or when you have a special check instruction, or there's another load you can put there that'll re-execute the load if the original load didn't work, a non-speculative load to the same value. OK, so why is this propagation of not a numbers important? Well, this allows you to pull code down here up and above this branch also. So we can pull the load up, we can pull dependent instructions up, and then just as long as we do the check at some point, and check to make sure that the load didn't take an exception or not a problem, we can basically speculate that the load is fine. We can speculate that the instructions dependent on the load are going to be fine. But if any of the dependent instructions on the load are not fine, that we've also speculated, when we go to, at some point in our code, we need to introduce this check instruction here, which sees if this value is not a number. So if it propagates all the way through your code, you have a load, a add, a sub, which all reads and writes, let's say, register, or somehow reads from register 1, and there's sort of a dependency tree from register 1 through that code sequence. At some point, you want to check after the branch has actually happened whether everything's OK. And because it all propagates, you can basically do work early and then check later. And when you do the check later, you can say, oh, I get it, everything's OK, and it has a value in it. If it has not a number in it, or it has this poison bit set, and it's propagated all the way through, at that point, and you can jump to fix-up code, which you can re-execute the load and all of the code you've pulled up, all that speculative code. And that's why you need fix-up code and not just re-execution of the load. because the fix-up code might have to re-execute more than just the load. It might have to execute the load and all the code, the other code you pulled up in front of the branch. OK, so let's move on to another type of speculation, and this is data speculation. So in data speculation, our problem here is we have memory hazards that are going to limit our scheduling, especially if we have to do all the scheduling statically. So if you're conservative in your compiler and you can't prove anything about the different addresses, all of a sudden what you have is every single load is dependent on every single other load, and every single store is dependent on every single other store. Now I might say, why are loads dependent on other loads? Well, though loads and loads you might be able to reorder pretty easily, you have to worry a little bit about if one takes a trap before the other. I guess we could have already talked about how to solve that problem. But once you reorder a load in a store, then you start to have problems. Or reorder a store in a store, or anything with a store, then you start to have problems because all of a sudden you have some state that changed in your memory system that you have to make sure that in original program order, the later instructions actually pick up the result of that. So later loads or stores somehow honor the results of that. So it's really sort of focused on moving loads and past stores. So what's our solution? Well, our solution is to add some hardware check to guarantee that the pointers or the two memory addresses, when you do the reordering of a load in a store or a store in a store, that these addresses are not the same. And this is actually the same thing that we did in our load store queue or our load store memory disambiguation that we talked about in out-of-order processors. So it's the same sort of thing going on here. But we need to actually change the instruction set to handle this in a VLIW setting versus in the superscale where it was all microarchitectural issues, sort of below the instruction set that no one ever had to look at. OK, so let's look at how to do this. We have a code sequence here, some instructions, a store, and then a load. Compiler can't prove anything about these stores and this load. But in an out-of-order superscalar, it could guess or speculate that the load and the store don't share the same address. And if they did, it could basically roll back the code and re-execute the load. And we want to emulate something like this, but doing it all statically with the compiler. OK, so how do we do this? Well, this is something else that Itanium added and was also talked about in previous research VLIW processors or explicitly parallel instruction set processors. What you're going to do here is you're going to move the load up above the store. And this is basically speculating that the load and the stores don't hit the same address. And much the same way that when we reordered loads above stores in an out-of-order superscalar, added the load address to a load store queue and a memory disambiguation queue, we're going to do the same sort of thing here. That when we move this load up, we're going to have a different instruction here of load and add. So what this is going to do is it's going to add, it's going to do the load and add the address to a special table, which we're going to call the address, what does ALAT stand for? Advanced Load Address Table. The ALAT is what Itanium calls this. So it's a structure that's a associative structure where you can put addresses in it and then check other addresses from other instructions against it. And if you get a hit or something like that, you know that something bad happened. And you can re-execute. So we're going to see here that we're going to have a load, which is going to get the load out in the memory system. We could overlap the time in the memory system with executing other instructions. We have a store here. Now, the store is going to take the address of itself, and we've changed the instruction set here because we added these two new instructions here and changed the semantics of a store. And it's going to check in the ALAT, or the Advanced Load Address Table, to see if the address the store is happening to is already there. And if it is, it's going to change the table somehow. And we'll talk about that in a second of what exactly happens. But roughly, it's going to take this address out of the table. And then when this load check happens here, this checks to see if the address is still in this table. And if it's been bumped out of the table, it jumps to fix up code, which is basically going to re-execute the load, or re-execute the load and all the dependent instructions on the load. So we can effectively do data speculation, but all in software. But this is going to require us to have an associative hardware block or some sort of content addressable memory, a CAM, that we need to add that all load addresses and all store addresses are passed across. And this is similar to how we had our memory disambiguation queue in our out-of-order superscalar. OK, so let's look at the ALAT, the Advanced Load Address Table. OK, so what do we have in here? Well, 3 things. We store the address. We store the size. This is important so we know, is it word, double word, half word, byte, sort of thing when we go to do matching. And when a load.a happens, it adds 1 into this table. And we denote the register number that is the target of this also. It's kind of useful to know when we go to do the check. This is to match up to make sure that the same load is the same load from before, and we can effectively remove the address from the table when we do the check. OK, so we added an address. OK, we're running along. And no, we execute stores, but the stores don't hit on that address. So when a store executes, what is it going to do? Well, it looks in this table and cams or does a comparison against all of the addresses with size matching and everything against this table. And if it's in the table, it removes it from the table. So by the time that the check or the load check happens, that address is not in the table then. So when the load check happens, it's going to look in here, this table again, and say, oh, I'm not in the table anymore. This address is not in the table anymore. So at that point, you can know, let's go re-execute that load. But if it's still in the table, that means no stores bumped it out of the table. So no stores in the interleaving time bumped it out. So the speculative load was fine. So we've effectively done what out-of-order superscalars can do. We can move now loads above stores. And through a change to our instruction set architecture, by adding these special check and load check and check instructions, and by changing the semantics of load and adding a load add, or load A instruction here, we can change, we can have data speculation into our program. OK. A couple other things that are fun to add to classical VLIWs to improve performance. I just kind of want to breeze through these next 2 ones a little bit faster here. First one, multi-way branches. So problem, you have a VLIW architecture or a very long instruction word architecture. And if you have, let's say, 10 things in one instruction, or 10 operations in one instruction, or 10 operations in one bundle, but you have sort of short branches, or maybe you have multiple branch decisions happening. You want to have sort of a branch every 3 instructions. Well, you have lots of wasted slots. If you can't somehow have one instruction branch multiple directions, then you might say, branching multiple directions, that's a really weird idea. How do you have an instruction go multiple ways? I thought branches could go 1 of 2 places. They could either fall through or go someplace else. Well, we can actually change the instruction set to have a branch that can go multiple directions. So let's look at this with a full predication example here. So we have 2 bundles of code here. This first one here is 3 instructions in it. These are all executing in parallel. And what this is going to do is it's going to do 3 different comparers. So this is similar to this is our full predication example here. It's going to write to these predicate registers with the logical positive and logical negative sort of versions of the predicate comparison. OK, so that sort of stages us to do 3 different branch comparisons. And then down here, we have 3 branches that all branch based on this predicate, or these different predicates that we already staged or set up here. And they can branch to 3 different places: label 1, label 2, and label 3. And there's also could be fall-through code if none of the branches are taken. And one little wriggle here that you have to sort of figure out the semantics, and I should say Itanium actually supports this, so you can buy real chips with this in it. If you have 3 branches together, you need to somehow order these branches, because let's say they all say taken, well, or they all resolve to actually being taken, well, which one do you take? Because you could branch to all 3 different places, and we want deterministic execution. So typically when you have an instruction set like this of multi-way branching, you define some order. Maybe the first one has priority over the second one, which has priority over the third one, et cetera.